and the whole thing, actually all three steps are Vigenere. This final goal. And if you're not familiar with this cipher, the idea is have hello world. Yeah, they use different keys. And we, for example, have the same alphabet as before, assuming that our capital and small characters are of the same kind. So the simple alphabet, not the extended one. And let us say our key is no longer a number like 3, but a sequence of numbers. For example, 1, 2, 3. So we may represent that key word, assuming that 0 is A, 1 is B, and so on, 25 is Z. So in this case, our key would be BCD. Of course, it can be some meaningful word, not just combination of characters, but this is just an example. And when we'll be encrypting or decrypting the text, we want to apply the same approach as we did with the Cipher, but we want to wrap the key around the text. So in other words, to encrypt the first character, we use the key value of 1, then key value of 2, key value of 3. 1, 2, 3. And then for the second L, there will be 1, 2, 3. 1, 2, 3, 1. So, for example, H will become I, E will become G, L will become O, L, M, X, Y, Z, O, P, P, Q, R, S, L, M, and O, D, E. So this is encryption and decryption. If we know the key. The whole purpose of our development is the Vigenere cipher. Breaking of the Vigenere cipher is way more challenging task because it is not possible, actually it is possible, but it is much harder to apply statistical analysis to this text. And the problem actually comes from the standpoint that for the pure statistical analysis, we don't know the distribution of cryptographic key is pseudo-random. So in other words, this is the result of encryption with one key, this is the result of encryption with another key, this is the result of encryption with the third key. Of course, if we know, for example, length of the key, we can certainly state that the fourth letter of the ciphertext is encrypted with the same key as the first letter. And for example, the seventh letter is encrypted also with the same key. But once we start, once we're given with the ciphertext, we don't know neither the key or, better to say, its components. Neither we don't know the length of the key, which is important part of the process, of the breaking process. So let us first assume that length of the key is somehow available to us. So from some source we, for example, know that for that cipher text that we have intercepted was obtained by utilizing key with the length of three characters. What we can do in this case, we can break the given cipher text into groups, assuming that each group is encrypted with the same key. So in this case, we can form group 1 comprised from characters I, M, P, E. G2 will be G, Q, T. And G3 will be O, Z. How many groups we're going to compile? Same as the length of the key. So if then we're going to compile 3 groups. So the question is still yet open. How do we know the key? And let us keep the question open for a while. Let us assume that we know length of the key, and that's the. Now, if we look at each of these groups, it is not a recognizable English text, obviously, because there is a gap between I and M. And there is no chance that any of these groups can be recognized as English text. But statistics used within each group is the same as we experienced when we were working with the Caesar cipher. Because as long as each group is enciphered with the same shift, so that's pretty much the same situation when we were given with the cipher text, which was entirely encrypted with the same shift. If the group is long enough, it's supposed to contain enough statistics for us to break individual group by applying Caesar breaking algorithm. By breaking the group, so let me just Caesar breaker. We're going to recover the corresponding plain text group, which was H, L, O, D. And the key value of 1. It's not going to happen for the short group, because 4 characters is obviously not enough for the statistics to show up, for statistical patterns to show up. But if it was a longer text, we definitely can apply Caesar breaker and recover plain text associated with this group and value of the key. So we can recover the first group, we can recover second group, we can recover the third group. So for example, group E, O, R, and this one will L, W, L. This with the key of 2, this with the key of 3. And I know that these are versions of the plain text. But in reality, you can use the Caesar breaker algorithm and just recover those groups of keys. So the only thing you need to do at the end is to put together all these recovered groups and the original text. So H, E, L, L, O, W, O, R, L, D. Hello world. This technique works if we make 2 assumptions. The first one I already sounded, And it is about us to know the length of the key. That's the crucial point, because we use length of the key to break given ciphertext into groups. And the second assumption is that reconstruction attempt, which appears with the first rank, is the correct recovery. You remember that when we break, actually encrypt hello world, that's example is shown on the slides. Hello world with the Cipher with the value with the key equal to 3, it is equal to horse rock, and then we try to break it. The correct reconstruction shows up on the third place. In other words, the first reconstruction attempt, the most likely correct reconstruction attempt, is not correct in fact. And this behavior will be shifted towards correct result if length of each group is sufficient. So we probably can say that if length of the group at least 20 characters, you probably can vary it to 15 or to 25. It depends. But 20 characters usually show good reconstruction with the Cipher breaker. So if each group is comprised from 20 characters, then we have a good chances that correct reconstruction attempt will be on the first rank, on the first place. And we will be able to correctly recover the plain text for each group and corresponding value of the key. Assumption. We want to introduce a constraint to the text, which must be met before we even start working with this. If we assume that length of the key is and 20 at least in each group, then 3 times 20 is the minimal length of the ciphertext that we can deal with. So if someone gives you a ciphertext of the length of 10 characters and tells you that length of the key is 7, no chances you can break it. Only sufficiently long ciphertext can be broken. So the last part that we are still missing is how to guess length of the key. And guessing length of the key is very important part of the Vigenere breaking algorithm. It is one of the most challenging part, because breaking plain ciphertext into groups and breaking each group to recover plain text representation along with the corresponding key value, it's not a problem. We already have this Cipher breaking algorithm. But what about guessing the length of the key? It's what? How can it help us? So you want to try key value, key length equal to 1, 2, 3. And how would you guess about correctness of reconstruction attempt? Have in mind that we're trying to develop a software solution which is not associated with a human judgment about its quality. So we develop it once, then we feed some ciphertext into it, and we have no control. It's supposed to report us with the plain text. It is not like it gives us something to check. Does it look like English? It's not a correct assumption. It will make ahead of time if it's long enough. So if we, for example, okay, length of the key equal to 1, we form one group, we try to break it. Actually, we break it with the scissor, and then how is English? So far we did not develop any measure of the language. We've developed properties of the language, but not the opposite. Where we don't have any way to look at sequence of characters and to state whether or not this sequence of characters is English language. Because for us, sequence of characters can be just random sequence of characters or may have some statistical properties. So evaluation of the length of the key is purely based on statistical properties of English language. And not necessarily it needs to be English. Same as we used statistical properties of frequencies of appearance for individual characters, that is the same approach, but expressed in slightly different form. That number 3 can be guessed by looking at this particular set of characters and stating that more than likely length of the key was equal to 3. Of course, if the length of the ciphertext is not sufficient, of the entire ciphertext is not sufficient, when we don't have enough statistical data, then our prognosis will not be correct. But if the ciphertext is long enough, there is a good chance that whatever we're guessing is the correct value. And we're going to work through the procedure which allows us to evaluate length of the key. But before we switch to this procedure, let me ask you if this is clear. If this is the only missing part of the puzzle, and the rest you understand. All right, that's good. So, consider is how to whether or not sequence of characters represents English text. Alternative to having English text in front of us represented by a sequence of characters is to say that it doesn't have any pattern. It is, for example, distribution. Say I just want to write down 20 characters from the alphabet. E, F, Z, F, I don't know, P, Q, R. What is the chance that this sequence is English? Chance does exist, but it's really low. But what if we randomly choose a paragraph from some text? So our choice is random. We randomly choose a paragraph. But sequence of characters actually represent the English text. So in other words, that sequence of characters, for example, this is a sequence of characters. We can take a look at this sequence and say that, for example, character E appears oftenly than other characters. That fits in well with the statistics of English language. That, for example, character Z doesn't appear at all. If it was listed here, probably it would be listed once compared with other most common characters, its frequency of appearance of z or x will be lower. So there is some approach for us to judge whether or not a phrase or a sequence of characters is English. We're actually not that much interested in sequential property of this set of characters. But what we're interested in membership of particular characters in that phrase. So if you count number of i's, number of a's, the correlation with English language will be high for this set. So what we want to do is compare these two sets in order to judge whether or not particular set is English. We want to compare this not with English at first, but with the random sequence. If the sequence is purely random, how can we judge for the frequency of appearance? What can we say about the frequency of appearance any given character, for example, character E, in a purely random sequence, or in a purely random set, better to say? Can we say the probability to see character E in the random set is the same, so probability to see E is the same as probability to see X, or probability to see Z. It is the same probability because we just randomly generated the sequence, and of course it will depend on what is the properties of our random number generator. But if it is normal distribution, for example, then all these probabilities will be equalized. So probabilities are the same. We know that probabilities of characters in this alphabet will not be the same. So what if we can pass the set of characters through some filter that will judge for the, not the randomness, but non-uniformness of distribution of the characters. So in other words, if we consider some text and try to build, try to draw a plot where on the x-axis we will have all the characters, A, B, C, all the way to Z. And on the y-axis we'll draw either number of appearances or relative frequency, which is measured by 1. So with the random text, there will be very minor fluctuation around some mean value. With the determined text, we know that E value will be higher than, for example, G. And then X will be even less than that. So it will be greater fluctuation. If we just consider the sequence A, B, C, D, F, G, all the way down to Z, 26 characters, and for example repeated multiple times, it is not random, but for sure every character is listed exact same number of times. That is just the case. So in this case, we will have perfect flat line to the number of distribution. So what the method of key length evaluation is of steps. The first step, we should develop a procedure that will tell us how likely set of is. Actually, we're not that much interested in judging for a set of characters to be not random, but to be as close as possible to the distribution which is associated with the English letters. We know that for character E in 1 gram table, if I'm not mistaken, it is 008, the relative frequency. That's what we can find on the set of slides. You can come up with your own 1 gram table, but character E probably is the leader in this scenario. What if we draw the picture of distribution and we'll try to express that picture in just one number? Once again, instead of thinking of the measure of the alphabet as a set of 26 numbers as represented in 1 gram table, let us now think of this alphabet, or think of the measure of the English alphabet as associated with just one single number. So we will have a single number to be associated with English text. We will have one single number to be associated with the pure random text. We will have one single number to be associated with A, B, C, D, E, all the way down to Z sequence. And any arbitrary text that we want to consider will be arranged somewhere in between this distribution and that distribution. So if we apply the same procedure to evaluate that value associated with the given text, then we can compare that value to be close either to random distribution or to English distribution. One value. If it is close to the English, we make a decision that given set of characters is English. If it is closer to the random distribution, then we state that given set of characters is random, not English. And the question now is, how can we come up with that single number? The single we want to evaluate based on, for example, starting from the 1 gram distribution. So this is 1 gram table, and it shows us frequency of appearance in a normal English text. So I think I was mistaken saying that for E we have 0080, so it is 0130. And I believe different sources you will find different statistics. But this could be considered as the good example of distribution of characters in normal English text. And as I said before, here we've got 26 values. It is hard to operate with 26 values, but it would be much easier if instead of 26 we'll have just one. So let us try to come up with a procedure of presenting that information in form of just one number. What we want to do, we want to find, let us say, for each of these characters, pi, we will have a probability. So let us say probability of seeing character A is this. We just name this specifically, because so far these are just numbers associated with characters. But we can name PA is equal to 0.080. PB is equal to 0.015, and so on. let us just add up all these numbers. What will be? Then we test to see whether or not some random distribution. Forget about image. And we just generated or have retrieved from calculate individual frequencies and apply the same procedure to for sure it will be 1 because relative frequency, that's the way how it is calculated. Each of these numbers can be represented as number of times when, for example, character D appeared in some text divided by total number of characters. That's pi of I, P of I, or P of D, I'm sorry. When we'll be adding all these p's together, then n will remain in the denominator, and then nd plus na plus nb plus nc, in sum, they will give us n, total number of characters. So it is structural property of the sum of frequencies to be equal to 1. Doesn't matter what distribution we are talking about. So far it doesn't help us to judge whether or not set of characters is random or English. But what if we try to compare any given set of characters with a distribution of that sequence, A, B, C, D, E, all the way to Z. In other words, let us consider that set of characters nicely ordered, where PA equal to PB equal to PC equal to 1 over 26. So here I use 26 because our alphabet is 26 characters. In your assignment you will have extended alphabet, so it's not going to be 26, it's going to be 77. But let us say we now consider that set of characters. That each of these frequencies is 1 over 26. Obviously that still is equal to 1. Not because it is special case 26 is 1, but because of the way. And now we want to calculate the one we are given for analysis. Say the distribution. How is the equation with this on this plot, where we have A, B, C laid down on the x-axis, and on the y we have those PIs. Because this is the level 1 over 26. If you divide 1 by 26, it will be, if I'm not mistaken, 0.038. Right? For example, character A is 0.08. And 0.08 is somewhere here. So that's our A. It will be above the level of 126. Character B is 0, 0, 15, it is less than this, twice less. So that will be our character B. That's the point. All right? With the pure random distribution, we know that more than likely the fluctuation is less. So the distribution will be around 1 over 26. And that's how we're going to judge how much the given distribution is, how much the given set of characters is different from this flat line. To calculate it, we can do just that. Instead of adding up numbers p of I, which is always equal to 1, we can do this. So how much every given pi is different from 1. And to have we will add the sum of p of I plus 26 sum of 1 over 26 I from 0 to 25. Minus, I'm sorry. So we know that this is 1. And if we calculate this, it's also going to be 1. This is always equal to 0. Doesn't matter what distribution we have. Doesn't matter whether or not it is random or English. So we cannot rely on just pure differences. So they will compensate one another. But what we can do to actually calculate how much given distribution is different from the flat line, we can calculate sum of squares. In this case, each term will be positive. Other terms will not compensate for it. The flatter the distribution, the closer each pi to 1 over 26, the less number we will get here. The higher the fluctuation, the bigger each term will be. The larger the sum will be compiled. So the value will be larger for the large fluctuation and smaller for the small fluctuation. In case of pure random distribution where each pi is close enough to 126, this will tend to 0. It will be small positive number, but will be really close to 0. In case of A, B, C, D, all the way down to Z distribution, it will be equal to 0. Because each of these is 1 over 26. So each term will be 0. And let us now calculate, actually open up this parenthesis. Pi minus 1 over 26 squared. We keep squared minus 2 over 26 times pi. And everything in parentheses. So I just put up this parenthesis. Minus 2 over 20 times sum of pi That's for the second term. And finally, plus sum of 1 over 26 squared. We cannot say anything about the first term. So we want to keep it, pi squared. We know that sum of pi's is equal to 1. So from the second term, we've got 2 over 26. From the last term, sum of these constants will give us 26 constants of this kind. So 26 divided by 26 squared, it will be 1 over 26 plus 1 over 26. So in this case, we can cancel one of these and make it to be 1 over 26. So this is the formula that shows us how much a given distribution is different from the flat line. And the flat line, I remind you, it is A, B, C, D, E to Z or pure random. This is ideal case. This is the real case that comes as close as possible to the ideal case. In case of ABCD or flat line distribution, this, each of pi's is equal to 1 over 26. So 1 over 26 squared sum will give us 1 over 26 minus 1 over 26. Result will be 0. So for the flat line, it is 1 over 26. Of English alphabet, where each of pi is sum squared, the will be 0.67. So if you just from one table, and we'll calculate this measure, then we'll similar to this. Of course, different sources will give you different 1 gram table with slightly different numbers, but you will get numbers similar to this. 1 over 26 is approximately 0.0385. So if you subtract one from another, you will get a certain value. Now, how this helps us to judge for the alphabet? Actually, we already judged it, because we know the random distribution will be associated with which value? We know that the flat line will be 0. The pure flat line, the theoretical flat line, will be associated with the value of 0. Pure English will be 0.067 minus 0.0385, whatever value it is. If I'm not mistaken, it's 0.027 or 28, something. We're not that much interested in this particular number, but you just want to subtract that from this. Whatever value you will get, it is the one for English. So pretty much any given text that we want to analyze can be passed through this procedure. For any given text, we can calculate sum of pi squares. And then subtract 1 over 26 and see how close that either to 0, which is the measure of to that difference, which will mean that it is we could, if it is close to the 0, any to operate with this. Usually in the literature they operate with two formulas. These over 26. And this is what is called index of coincidence. You may find two versions of index of coincidence definition. In some sources, sum of pi squares, it's index of coincidence. And that's the value for English. The value for flat line text or the random text will be 00385. In other words, 1 over 26. So that is English, that is random, and then we just decide which one it is. So if we have something about 006, then probably we can guess that it is English. If we get something 004, then it looks more like random. But it's not convenient to use that measure because it is on the second place after the decimal point, the entire distinction. It's just not convenient to analyze. That's why this measure is introduced, and oftenly this is called index of coincidence. I will tell you in a moment why it is called index of coincidence, but let us just consider this as alternative measure that we want to have in mind. And this is an attempt to normalize the value of index of coincidence. Normalization is important because after doing this, we no longer operate with small values. For example, we know that for the random distribution, this will be 1 over 26. 1 over 26 divided by 1 over 26 will result in the value of 1. For set of text, for random set of characters. That is much rather number. What about English text? For English, this value is 67 divided by 00385 will be 1.73. And now, again, we want to find how close the distribution is either of the two. But with this approach, we have one great benefit. If it is greater than 1.73, in other words, it appears on this side of the range, for sure it is closer to this rather than to this. So if it is 1.73 or greater, it is English. Or at least maybe something that makes sense. Maybe some European language with the similar distribution pattern. It cannot be less than 1, by the way. But it can be in the range from the 2. So that's what we want to do. We're given with a text, and we want to judge whether or not it is English. We calculate sum of squares of frequencies, and then divide it by 1 over 26. Division by 1 over 26 simply means multiply by 26. And depending whether or not it is close to 1 or to 173, we can judge for the nature of this set of characters, if it is English or not. How does this help us to evaluate length of the key with the Vigenere? And this is just utility to be used, and the use is straightforward. You remember the groups that we were working with? And it was sounded that why don't we just try key length equal to 1, key length equal to 2, key length equal to 3. In fact, that's the right approach. But now we have the mechanism to say that length of the key equal to 3 actually is the correct one. Because if we try key length at some point equal to x, group 1, group 2, all the way up to, and each of these groups will have certain number of characters. All of the characters in any given group were in Cipher does not affect if the group is long enough. In each group we should see exact same distribution as with English. If it is the group that corresponds to the correct length of the key. So in other words, we try all possible values of x. 1, 2, 3. We probably want to stop when length of each group will be less than 20. So if our Cipher text is 1000 characters, we probably can try x all the way to 50. Assuming that the length of the key is 50, which is a good key. And it is hard to actually to imagine that Vigenere is encrypted with the key of 50 characters can be broken. It can be broken if we have enough statistical data. So if the length of the Cipher text is 1000, length of 50, it's processable. So we try all this, we form the groups. And then we feed these groups through that approach. For each group, we calculate index of coincidence. And then we probably can find the mean value for index of coincidence for all groups. And if mean value is close to 173, then we make a decision. The key length was on this particular iteration was guessed correctly. If the mean value of indexes of coincidence is closer to 1, then it is not the case. If it is greater than 73, then if key, for example, if key length was equal to 3, length for the x value equal to 6. So any will have the same in the same good quality of number that corresponds to so once again the approach we're given with the cipher text. We probably can skip key length equal to 1. We try key length equal to 2. We break the text into 2 groups. We fit each group through this algorithm just by calculating index of coincidence. We calculate mean of these 2 values. And if it is close to one of these, we make a decision whether or not each group is English. Actually, it's not English, but has the same statistics. If it is not close to 173, but in fact closer to 1, we continue. We try x equal to 3. We break the cipher text into 3 groups. And then calculate index of coincidence for each group and minimum mean value compared against this range. And so on and so forth. So we want to repeat it. As you can see, the quality of this analysis is purely based on how we're going to judge for the position of the mean value with respect to that range. So if we'll have, for example, x equal to 5, the value will be 1.6, but x equal to 6 will give us 1.8. We should prefer x equal to 6 because it is the other side, it's on the other side of the boundary. So distance to 173 is less than distance to 1 in case of x equal to 6. Even though both of them looks pretty close to 173. This is the more preferable option. And then get the length of the key. We just want to apply to it and break the Vigenere cipher. So breaking of the Vigenere cipher is actually and then apply the breaking algorithm multiple times. Do a of break this system are a software called Octave. You're probably familiar or have heard of a software called MATLAB. So that's very famous in engineering business. So Octave, it's open source analog of MATLAB, and they claim for more than 90% compatibility with MATLAB. In fact, some features of Octave make it even more convenient for us to use in this class. And I will show you how the entire Vigenere breaking procedure can be applied, can be actually implemented in Octave. So we'll end up with a working set of functions which will be applied one by one, and then we'll be given with the cipher text. As the result, we'll have the plain text that corresponds to that cipher text. So we'll do it on next Monday. But think about this approach, finish your step 2 implementation, and I promise you to tell you why it is called index of coincidence, because it doesn't make sense just to have some value and call it somehow. So index of coincidence It is called mainly because of this power 2. So if we have, for example, pi is the probability to see character, or let me say pa. It's a probability to see character A in certain set of characters. Then we can say that pa squared will be probability to see 2 character. Assume that more than one does exist. So if it is long text, and we are given the probability of a single character, then we will see 2 characters of the same kind will be pa squared, pb squared. It is probability to see 2 characters b in that text. If we add up all together, pz squared, so that's the formula. It is probability of in the given text without specifying what character we are interested in. To see 2 characters of the same kind, in other words, to see the incident of repetition, index of coincidence. So this is just why it is called that way. We divide it by 126 for the reason to normalize it, but I would call this value as modest index of coincidence rather than this one. But in some literature sources, this value is called index of coincidence. All right. Should you have any questions? No? So that's all for today.